Hey everyone, how's it going? This is my Physics 2211 lab for oscillations. Here we have our table of contents that just shows a few things that we've been going over. We have our introduction, our principles, initial conditions, our tracker data, the code, and then our analysis and what if at the end. Here's our introduction. The purpose of this lab is to observe the motion of a spring mass system with the mass in an oscillating arc. We use tracker for our observational data and GlowScript for our computational model. Our goal is to determine whether the acquired model follows the energy principle. And for a brief preview of the results of the lab, it was determined that the system's total energy remains at a constant zero, which does depict the energy principle. So here we have a few key principles and concepts we need to go over. Here we have Newton's second law. First off, this is a very basic principle that we include, and we've gone over before. We have our update formulas right here. We have our velocity update formula, and then our position update formula right here. And then we have the law of conservation of energy, which is important for this lab. Here's some more initial conditions right here. We have our potential energy formulas right here, and then here's our initial conditions. Here's our model of the forces right here, and a few equations that we need for our code. Here's the tracker model right here. We can go ahead and play that out. And as you can see, as it oscillates right here, we have our X and Y data that is compiling right here. And it shows the oscillations up here in our graph. So starting off with our code, first off we take our X and Y data that we got from our tracker data, and then we plug it into the code right here to actually spit out our data from the code. And so in line 79, this is our gravitational constant, and line 82 is our spring constant, and we calculated it using this right here, and we ended up getting 6.88 newtons per minute. Line 85 is the relaxed length of the spring, which is calculated by these equations right here. Here's some more of our code right here. Line 88 through 90 includes our spring length values. The initial energy equations are included in lines 93 through 96. The while loop begins on line 105 and includes several force and movement equations, and along with the value 9.524, which is the length of our tracker video. And the lines 124 and 126 include the velocity and position update formulas respectively. And here's our code after it runs. And you can see we get our oscillation motion right there. Our change in energy versus time graph. X position, Y position. And yep. And talking about our computational data results, there are a few sources of error that we need to take into account. The system is not isolated from the surrounding in real life, meaning that there will be work done from the surroundings. Human error in the center of mass placement and tracker, that could always go wrong, which causes the variations in data that you see here. Here's our change in energy versus time graph. It shows that the change in energy of our system is equivalent to 0, and that's exactly what we needed to see. So is the energy principle satisfied? Yes, it is. This is because the change in energy of our system is equivalent to 0 as shown in the change in energy versus time graph that we just discussed. And our total energy is kinetic plus UG plus US equals 0. Oscillation estimates. So after we looked at our X position and Y position time graphs, we see that the oscillation period for the X position graph is close to 1.7 seconds, while the oscillation period of the Y graph is close to 1.5 seconds. And looking at this information right here and the differences, we can conclude that it is best to calculate the spring constant using oscillation periods of not just one axis. And as you can see here, if you look at our X position versus time, you can look closely and see that it's 1.7 seconds. It's about 1.7 seconds between each oscillation right here. And then on our Y position, you see that it's about almost exactly 1.5 seconds of difference between the oscillations in this graph. And that's it. That's about all I have. Thank you for watching.